So we're just not going to do this halfway. We're going to try to do the whole thing all at once. This video is long, and it's all about avoiding awawas. So there are several interesting places to start. However, as I have learned from some of my instructors, sometimes the best places to start are those where we have the most tangible examples. So in 1886, the first World Championship chess match was played between Wilhelm Steinitz and Johannes Zukertort. The match was a first to 10 wins competition under rules agreed upon by the pair. Rule 13 in the list from the German handbook on the game stated that if both players repeat the same series of moves 6 times in succession, then either player may claim a draw. Now, the inclusion of this rule probably seems straightforward. You don't want two chess grandmasters just repeating moves that don't evolve the state of the game so that they can artificially stall their time and figure out what they want to do next. You want gameplay to continue forward in time. However, your rules for a particular game should do 2 things. So 1, you don't want your rules to trivialize or dilute the intended complexity of the game. And 2, you want to make sure that whatever rules that you have in place actually end the game. So there are several reasons why you would want something like a Rule 13 in place of, say, a move rule. A move rule in chess would be something like a set number of moves without a capture ends the game in a draw, or some other notion of ending the game based on number of captures of each opponent. These rules are implemented in some cases nowadays, but they prevent the game from achieving all of the possible complexity that it has. But that's not really the point of this little tangent here. The point of this tangent is to ask the question, do we actually need a move rule? Do we need to cut the game off at a certain number of moves without a capture in order to make sure that the game ends under this Rule 13? So the answer to this question about chess connects a variety of fields of mathematics, ranging from, well, of course, theoretical chess. The guy who published a paper showing this answer to this question was a chess grandmaster, and he actually published a math paper about it. And then also combinatorics, number theory, dynamical systems, and fractal geometry are all sort of linked together by this question in some sense, or at least the answer to it in some sense. So in order to talk about this thing, I need to sort of just start in the middle. So the first character in this story is that of Axel Thue, who was a Norwegian combinatorialist. He studied in particular and focused on the combinatorics of words, or combinatorics of sequences. And he was focused primarily on binary sequences, or at least that's what he's most famous for. Just to define what he was looking at, a binary word or sequence is an element of the symbolic space 0, 1 to the natural numbers. That is, it's just a list of zeros and ones. So one of the interesting things about studying combinatorics of these symbolic sequences of zeros and ones is that these zeros and ones may not have any numerical information attached to them while you're doing this combinatorial study. This is important because this makes this study of stuff general enough that it can apply to various areas of mathematics later on, as we'll see. The first observation Thue made may feel obvious if you have done any work with truth tables or with symbolic dynamics or this combinatorics on word stuff. So in 2 of Thue's papers, one in 1906 and one later on in 1912, he noticed that for any finite binary word that had length greater than or equal to 4, there was always a square present, or a finite subword which, when repeated, appeared in the word. And then, as mathematicians do, asked a more general question, and that, is there a particular n that forces a cube to occur in a finite binary word? Thue's answer, which he proved, and which we'll prove in this video, requires a little bit of a detour through the world of binary numbers, and how concatenation can be translated into binary math. So to do that, I have to take a little bit of time to tell you things about binary numbers. If that bores you and you just want the punchlines, there are chapters all fleshed out below, because this is a longer video, so skip to where you may please. But I'm going to tell you about binary things if you're just continuing on. So the main tool in answering this question is to go ahead and look at binary expansions and how that relates to concatenation when you're moving from a number to twice it or twice it plus 1. So concatenation is exactly what you hopefully think it is. If you have two finite words, you just slam them together. You stick them together, and that is your concatenated word. Usually we just write words next to each other in order to concatenate them in the same way that you would write down a compound word in English. And on the board here, I have written this 0, 1 star thing. For those of you that are more algebraically inclined, this is just the monoid generated by concatenation over the symbols 0 and 1. In particular, the important thing here is that this guy, epsilon, is there. He hangs out. He will be used, sort of. He is the empty word, and he does nothing. He is the identity of concatenation. So it's just epsilon, empty word. It'll come up that we'll have a finite word that's length 0. That's the thing I'm talking about when that happens. But it's sort of a minor point, and you can get through most of the video without really thinking about that too much. And so we want to go ahead and compare the binary expansion of n and the binary expansion of 2n first. Well, the binary expansion of n is just the sum from I equals 0 to k of bi times 2 to the ith power. And that just means that the binary expansion of 2n is just twice this sum. But that would be the same thing as the sum starting at 1 and us adding a 0 to the end of that. And so we can go ahead and express 2n in the form of the sum I equals 0 to k of ci times 2 to the I, where ci is equal to bi minus 1 for I greater than or equal to 1, and c0 is just equal to 0. In particular, what this means is that if you take the binary expansion of twice a number, that's equal to the binary expansion of the original number, right concatenated with 0. A similar computation shows that when you look at the binary expansion of 2n plus 1, you end up with the binary expansion of the original number n, right concatenated with 1. And so this next thing is important because we're going to use it a ton in this video. But that is just that the observation you should make here is that n and 2n have the same number of 1s in their binary expansion, and that is strictly different than the number of 1s in the binary expansion of 2n plus 1. And in particular, they differ by just 1, 1, but I don't really care that they differ by just 1, 1. I just care that I do actually care that they are different by just 1, 1. Yes, they are different by just 1, 1, and that drives the entire ship to shore. Like, it's the whole, you could make it really not interesting and say that the whole video is about how 2n and 2n plus 1 differ in binary expansion in terms of the number of 1s by 1, 1. But there are so many other things to say about this. Okay, so with that, 2's question again was, is there an n for which a cube is forced to appear in a finite binary word of length n? And 2's answer was no. So here's the definition of the thing that is the punchline of this entire video. And there's so many things to say about it. It's very, very cool. This video, even though it's very, very long, and I'm going to talk about a lot of them, doesn't cover all of them. And I have sources below if you want to read more. But this definition is that of the Prouhet-Thue-Morse sequence. I don't really... he's a Eugene his last name. I don't know how to say it. A lot of people forget that he is a person that actually studied something and came up with a thing that is related to this, and we'll get to him. He was working in a number theory, and there's stuff to talk about there, but everyone forgets that he basically did this first. But 2 is the guy who wrote it down formally. So we're going to start with 2, and I should tell you what we already started with 2. So I'm going to tell you what the thing is. So the I don't know how to say his name. It's fine. The Prouhet-Thue-Morse, it's 2. He's Norwegian. It's 2. So okay. So the Prouhet-Thue-Morse sequence is the one defined in the following way. Let M be an infinite sequence of zeros and ones with the defining property that the jth term in the sequence is the number of ones that appear in the binary expansion of J mod 2. So just go through some of these examples, right? The 0th term of the sequence is 0 because 0's binary expansion is just 0. There are 0 ones, so mod 2 it's 0, and so we have 0. For the M1 term, or the second, but it's first because 0 indexing, it's important that we're 0 indexing here. It makes the arguments a lot smoother. Anyway, I'm usually anti-0 indexing, but in this particular case, it is helpful. So 1, the first term is just 1, and that's, again, because binary expansion of 1 is 1, number of ones is 1, mod 2, that's 1, and then for 2, binary expansion of 2 is 1, 0, so that's also 1. Binary expansion of 3 is 1, 1, so that's going to be 0. Binary expansion of 4 is 1, 0, 0, which is going to be 1. Binary expansion of 5 is 1, 0, 1, so 0, 6, 1, 1, 0, so 0, and then 7 and 8. And we can keep going on forever because each natural number has a unique binary expansion. So there's some immediate consequences of defining the sequence in this way, and the first one is that it's just an immediate observation from what we did a second ago with binary and concatenation. That is, if you look at the mnth term in the sequence and you look at the m2nth term in the sequence, they should be the same symbol, and this should be strictly not equal to the 2n plus 1th term. And further, we also have this recursive definition of how we could define this sequence based on this relationship between the nth term, the 2nth term, and the 2n plus 1th term. That is, the 0th term is 0, and then for every n greater than or equal to 0, m sub n is going to be equal to m sub 2n, and m sub 2n plus 1 is not equal to m sub n. Okay, but why does this work? So we have a definition, and I've told you a few things about it, and I want to tell you that no cube occurs in this infinite sequence, and I need to prove that to you. So I'm going to finally define what I mean by an awawa. An infinite sequence has an overlapping property if there exists a pattern within the sequence of the form awawa, or AWAWA, where A is just a symbol from whatever alphabet you're using, and W is some finite word formed from the alphabet that you're using. In this case, our alphabet is just 0 and 1. And so we almost have all of the tools required in order to prove that this word, or this infinite sequence of 0 and 1s, avoids an awawa. But I just need one more thing, and that's a derived sequence. And this is a sequence that you would form, like if you're studying an arithmetic, like not an arithmetic progression, but if you're studying a sequence that looks like it might have like a quadratic progression or other things like that, right? Where you go ahead and just add consecutive terms of the sequence. Because we're working in binary, we're just going to take that mod 2. So b sub n is going to be equal to m sub n plus m sub n plus 1 mod 2. The important observations about this derived sequence is that b sub 4n plus 2 is going to be equal to 0. And the reason for that is that 4n plus 2 in binary is just equal to, from what we did earlier, 2n plus 1 in binary, right concatenated with 0, and then again applying what we did earlier, this is equal to the binary expansion of n, right concatenated with 1, and then right concatenated with 0. So it's the binary expansion of n, right concatenated with 1, 0. Also, the binary expansion of 4n plus 1 is going to be equal to the binary expansion of 4n plus the binary expansion of 1 because that's just an expression of counting in binary, right? You just increment by 1. And so for n has the same binary expansion as n, right, concatenated with the word 0, 0. And then because we're adding 1, that is the same thing as the binary expansion of n, right, concatenated with 0, 1. And so from these two expressions of the binary expansion of 4n plus 1 and the binary expansion of 4n plus 2, we have that they have the same number of 1s mod 2. And so when we add those two values together, it'll either be a 0 plus 0 mod 2 or a 1 plus 1 mod 2, and both of those things are 0. Similarly, b sub 2n plus 1 is going to be equal to 1, because b sub 2n plus 1 is equal to m sub 2n plus m sub 2n plus 1 mod 2. And m sub 2n does not equal m sub 2n plus 1, so the possibilities there are 0 plus 1 or 1 plus 0, both of which are 1 mod 2. So the main theorem of this video, and which is going to run most of the other applications, is that M is an overlap-free infinite binary sequence. So the proof that I'll go through in this video is a little bit different than 2's original proof that M is a cube-free sequence. The one that I'll provide in this video comes from Christopher Williams' overview document on the subject. But as always, all of my resources and stuff are linked in the description or cited in the description below if they are not linked. The proof of this is actually really, really nice. It kind of follows an argument of how you would prove that the square root of 2 is irrational. It just focuses on parity of things. So even though there are a few cases, it's not super difficult to write this down given that we have this information about this derived sequence as well. So we go ahead and suppose not. That means that the Morse sequence is equal to awawa, which is just u, a finite word of zeros and ones, which has length greater than or equal to 0. And then your awawa, where a is a symbol from your alphabet 0, 1, w is a finite word of length greater than or equal to 0, and then v, which is just some infinite binary sequence that's tacked on the end of the overlap. There's a few things that we need to suppose here just to make sure that this contradiction goes through. And that's first off that this is the first place in which an overlap occurs. So some observations here is that we can go ahead and reformulate this idea of an overlap in terms of equality between positions in the sequence M. And to do that, we just have to give some names to things. So let's let the length of u be k, and then let's let the length of a w be equal to L. So k is greater than 0, and L is greater than or equal to 1. Because L is required to have a letter of the alphabet inside of it, and W and U are not, because they could possibly be the empty word. This lets us translate M is equal to awawa into the k plus jth position of M is equal to the k plus j plus lth position of M for every j, such that 0 is less than or equal to j is less than or equal to L. And writing just writing this all out to make sure that this makes sense. The 0th to the k minus 1th position of M are the first k positions of M. And so that would be your U, and then from the kth position to the k plus lth minus 1th position of M is your first AW, and then from the k plus lth to the k plus 2lth minus 1th position, that's another AW, and then lastly you have M sub k plus 2L, which is going to be your last A of the awawa and the uwawa, right? And then after that you just have V, and we don't care about V. V, it could be whatever you want it to be. It does not matter, because we care about this finite piece of M, because overlap has to occur in a finite piece of M. There are cases to consider, and there are 5 of them. It's going to be okay. There are 5 of them. Some of them are very similar to each other, but I will go through them just really quickly here. So let's avoid an awawa. So the first case is when k and L are both even numbers. In this case, we go ahead and let L be equal to 2L prime and k equal to 2k prime. then the overlapping property represented as positions in M can be represented as these equalities between these half steps. So if instead of having J, you look at J prime, which is the half steps from 0 up until L over 2, we have M sub K plus 2J prime is equal to M sub K plus 2J prime plus L. This implies that, well, using the definitions of L and K that we took because they're both even numbers, that M sub 2K prime plus 2J prime is equal to M sub 2K prime plus 2J prime plus 2L prime, and then using the equality between the number of 1's mod 2 in the binary expansion of 2n and n, we have that M sub K prime plus J prime is equal to M sub K prime plus J prime plus L prime, which is an earlier overlap in M, which can't happen because we assumed that we were starting with the first overlap in M. The next case is when K is odd, so the length of your U is odd, but L is even. So in this case, the argument is essentially the same. It's just that here, instead of taking K equal to 2K prime, we take K equal to 2K prime plus 1. And so then writing this out, we end up at the place of M sub 2K prime plus 2J prime plus 1 is equal to M sub 2K prime plus 2J prime plus 2L prime plus 1. And then since M sub 2N plus 1 is explicitly not M sub N, we get that M sub K prime plus J prime conjugate is equal to M sub K prime plus J prime plus L prime conjugate. Where conjugate just means that you flip the bit, or you take 0 and you replace it with a 1, or you take 1 and you replace it with a 0. But if your conjugates are the same, that means your original value was the same. So we have M sub K prime plus J prime is equal to M sub K prime plus J prime plus L prime, which again gives you an earlier overlap in the sequence M. So for the next three cases, this is where we're going to use the derived sequence B in order to push the argument forward. And they're not super difficult because you get to play with particular cases of L, and so you have a little bit more control over what positions you're talking about in M. So in this first case of where we have to address things with the derived sequence, or case 3 of this proof, we're going to go ahead and look at the case where L is greater than or equal to 5, L being an odd number, and K is just some natural number. So in this case, there exists a J between 0 and L for which K plus J mod 4 is equal to 2. This mod 4 statement might feel like it's out of left field, but it's really just some modular arithmetic stuff. K plus 0, K plus 1, K plus 2, K plus 3 all have different values mod 4. And the reason we're taking L greater than or equal to 5 and not L greater than or equal to 4 is because we've already covered the L equals 4 case. We just haven't covered the cases where L is an odd number, and so we're starting with L greater than or equal to 5, which is one of the cases where this sort of thing happens for odd numbers. And for all L greater than or equal to 5, where L is odd, you'll have this sort of thing happen where you run into at least a K plus 0, K plus 1, K plus 2, K plus 3, where you achieve all of the different possible values mod 4, which are 0, 1, 2, and 3. So if we focus in on this J for which K plus J mod 4 is equal to 2, from our properties of the derived sequence, B sub K plus J is going to be equal to B sub 4n plus 2 for some n, and that's just equal to 0. But K plus J is even, and L is an odd number. So K plus J plus L is odd. So B sub K plus J plus L is equal to B sub 2n prime plus 1 for some n prime, which we said was equal to 1 always. And so the awawa provides a conflict. So M sub K plus J equal to M sub K plus J plus L for 0 less than or equal to J less than or equal to L means that B sub K plus J should be, which is equal to 0, should be equal to B sub K plus J plus L, which is equal to 1. And that is a contradiction. The next case for L is equal to 3 and K is just some number. What we have here is that, well, now we miss one of the values mod 4, right? So we have a K plus 0, a K plus 1, and a K plus 2. But we must hit 3 of the 4 values. In any of those cases, once you've removed the value that's missed from the mod 4 set, you'll have a k plus j mod 4 that is in the set of 2 or 3. Now, if you're lucky, you'll just end up with k plus j is equal to 2 mod 4, and then you can apply the argument in the L is greater than or equal to 5 an odd case. But if that doesn't happen, you have to just be slightly more careful. So if k plus j is equal to 3 mod 4, then that tells us that, well, k plus j is an odd number, and we have that b sub k plus j is equal to 1. However, because k plus j is equal to 3 mod 4, k plus j plus L, which here is equal to 3, is going to be equal to 2 mod 4. And so that means that b sub k plus j plus L, which here again is 3, is going to be equal to 0. And the awawa again gives us the contradiction, because b sub k plus j should equal to b sub k plus j plus L, and that is explicitly not the case here either. Lastly, we have, quite honestly, the easiest case of this proof, which is when L is equal to 1. That is, your awawa is just an it's just 3 letters next to each other. And k is some just number, natural number, n. So in this case, m sub n is equal to m sub n plus 1, which is equal to m sub n plus 2. Yet, when n is an even number, from that first equality in the string, m sub 2n prime is equal to m sub 2n prime plus 1, which explicitly cannot happen. And for n odd, n is then some 2n prime plus 1, and we have from the second equality that m sub 2n prime plus 2 is equal to m sub 2n prime plus 3, which again explicitly cannot happen. So in all cases, m cannot have an awawa. That is, m is an overlap-free sequence of zeros and ones. So we're so far down the rabbit hole that I don't want to tell you about chess immediately. We're going to take a detour through some other applications and consequences of this avoiding an awawa thing, because it's just very, very fun. To me, at least. It's just like tickles the brain in the right way, and I enjoy it. So let's go ahead and just talk about what this does. Why do we care that we've avoided an awawa? So the first consequence of avoiding an awawa is that m is cube-free. And to see this is very quick. If you just write down a cube, which is just some word v repeated 3 times, then you can go ahead and break up v into having an awawa inside of it. That is, v0 would be your a, and then v1 to vn minus 1 would be your w for your overlap. Another place that this comes up is in the realm of symbolic dynamics. So an immediate corollary from this, or it's not super immediate, but it's relatively immediate in the grand scheme of things, from this overlap-free property of m is that there exists an infinite minimal symbolic dynamical system. I don't want to get too far into the weeds on the topological dynamic stuff here, but a minimal system is just one that maps into itself. So, and there is no subset for which you can restrict the dynamics and it will still map into itself. So the idea of how to show this is you go ahead and look at the full shift on 2 symbols, and we define a subsystem, which I'll call this fancy capital M, by the orbit closure of the Prouhet-Thue-Morse sequence. Because it's an orbit closure, it is a subshift of the full shift. And because M is non-overlapping, that means that each of its shifts are non-overlapping as well for every possible shift you could take. This means that there can't be periodic points in this fancy M shift because there's no sequence or subsequence of the orbit that gets close in the sense of agreeing on enough symbols to a periodic point. In fact, it doesn't agree with any periodic point up to a cube of the period. But every dynamical system has a non-empty minimal subsystem, which may be trivial. It might be the whole thing. And in this case, it is the whole thing, but it takes a little bit more work to show that. But so what we can say is that there exists some F, which is a minimal subsystem of this fancy M shift space contained in the full shift, which is minimal and infinite. And again, you can actually show that this particular f is equal to this fancy m. So that was just a couple of quick, immediate consequences of the Prouhet-Thue-Morse sequence being being overlap free, and right. So cube free is a consequence of that, and so is this symbolic dynamical thing that's relatively short to write down. But there are two other people associated to this sequence aside from Thue. So I want to tell you about them as well, because they did things in totally different areas of math, and it's kind of cool to see how it's all just linked together. All right, so I kind of went off on a tangent earlier about him, but Eugene Prouhet, why this guy? The story apparently starts with Euler and Goldbach back in the 1750s, just hanging out, sending letters back to each other. And there are two letters in particular of specific importance, which, side note, the AMS just has like a directory of all of these letters that are digitized that you can go look at and read, and you can feel really weird about why people talk about Euler and Goldbach as like doing a lot of really intense math. At least in these two letters, it feels not super great. I mean, sure, they asked really important questions, and there are some really cool things that they did, but in this particular case, I was really confused as to why some of the sources cited these letters as the foundation for this problem, when Prouhet does it in way more generality, even though he kind of got forgotten a while back. So the problem that I'm talking about is the classical Prouhet-Thue-Escott problem, which is a problem in number theory that Prouhet studies first in 1851, and again, some actually very impressive level of generality for the time. Terry and Escott don't tackle this problem until like 50 years later, or more than 50 years later, and they're looking at these problems of multigrades, or solutions to the Diophantine system, the sum from I equals 1 to s of xi kth powers being equal to the sum I equals 1 to s of yi kth powers for some k in the set 0, 1, 2, 3, all the way up to n. When you're looking at that type of system, it's very easy to think immediately that, oh, these just don't happen. In like highly non-trivial cases, there are no solutions. It would be absurd to think that you could do this for relatively large values of n. And the cool thing is that you actually can, and Prouhet proves this in his original paper from way back when. So let's just look at some solutions. So it's not trivial in terms of that it starts off the sequence of these non-trivial solutions, but it is trivial in the spirit of the problem. The first one being that 0 to the 0 is equal to 1 to the 0. And so this would be the case where n is equal to 0 and s is equal to 1. Next, we have 0 to the 0 plus 3 to the 0 is equal to 1 to the 0 plus 2 to the 0, and 0 plus 3 is 3, which is equal to 1 plus 2. This would be for n is equal to 1, and s is equal to 2. Next, we have 0 to the 0 plus 3 to the 0 plus 5 to the 0 plus 6 to the 0 is equal to 1 to the 0 plus 2 to the 0 plus 4 to the 0 plus 7 to the 0. And 0 plus 3 plus 5 plus 6 is equal to 14, which is equal to 1 plus 2 plus 4 plus 7. And then for the sum of the squares, we have 70 in both cases. And then just to sort of keep going and convince you that this happens and continues to happen, and we'll get to the more general statement in a second, but if you go ahead and look at 0, 3, 5, 6, 9, 10, 12, and 15 on one side of the equality, and 1, 2, 4, 7, 8, 11, 13, and 14 on the other side of the equality, this will be a solution set for n is equal to 3 and s is equal to 8. And so, like, how am I doing this? It's just the Prouhet-Thue-Morse sequence hanging out in the background. So if you look at the sequence, the first 16 terms are 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. And if you're looking at the positions of the zeros are exactly in the 0th, 3rd, 5th, 6th, 9th, 10th, 12th, and 15th positions. And these are all the numbers that occur on the left-hand side of the equality in the n equals 3 and s is equal to 8 solution. And on the right-hand side, we have all of the positions associated with ones. That is 1, 2, 4, 7, 8, 11, 13, and 14. Prouhet's name is attached to the Prouhet-Thue-Morse sequence because this pattern that we see here with initial segments of the Prouhet-Thue-Morse sequence and the solutions to these Diophantine systems was first discovered by Prouhet back in 1851. Now, he isn't actually the one to define the sequence. He only implicitly defined it, and that's why we started with Thue, because Thue is the first person to explicitly define it. But Prouhet's work predates Thue's work by over 50 years, and there's no evidence to suggest that Thue was aware of Prouhet's work on this classical Prouhet-Terry-Escott problem as we know it now. In particular, Prouhet proves the following theorem just in an equivalent wording, since the Prouhet-Thue-Morse sequence was not something that he explicitly defined. In particular, that the Prouhet-Thue-Morse sequence M has the property that for I being the set of numbers from 0 to 2 to the big N minus 1, such that M sub I is equal to 0, and J being equal to the set of J from 0 to the 2 to the big N power minus 1, such that M sub J is equal to 1, then for all 0 less than or equal to k less than or equal to big N minus 1, we have that the I's and the J's satisfy the Diophantine system described above in the classical Prouhet-Terry-Escott problem. So my French isn't great, and Eugene's paper is mostly in French, so I don't want to recreate the proof of this here, but it's kind of cool to go skim through the paper regardless of whether or not you have great French, because you can actually see where the initial segment of the Morse sequence is stated. Even though it's defined implicitly, he calculates the first few terms of the Morse sequence during his work on the problem. Marston Morse. Yeah, Marston Morse. Oh, no. No. You can't be in here. You can't be in here. Clyde. No. I have to go deal with Clyde. Okay, Clyde. It's gonna be okay. Just like... Hey. Well, dude. Go forth and prosper. Alright. Success. Alright, so that covers Prouhet and Thue. Now I just got one more dude to tell you about in terms of just why the sequence is called what it is. So Marston Morse in 1921 independently discovers the Prouhet-Thue-Morse sequence in his study of surfaces with negative curvature. In particular, Morse is working through studying geodesic flows on such surfaces, and just to give you some grounding bits / I don't know enough differential geometry in order to do this well, but I'm going to cite some things and go on some tangents briefly so that you have information if you want to read further. So for us, the curvature that I'm talking about is that calculated by this formula, which comes from the Bertrand-de Puiseux theorem, which is from 1848. This is referenced in Michael Spivak's 1999 textbooks on, or volumes, compendium of differential geometry. And side note, Michael Spivak has the funniest mathematician photo for a Wikipedia page ever. He's he's just doing differential geometry in the real world, hanging out, looking at tiny spaces. And his books for differential geometry are also just very fun. I've tried looking for these for research for this video, and I was trying to get a hold of a full set of them, and I've been having a hard time finding them. And they're apparently really good books for differential geometry, and they also just have really fun covers for a math book. They have really fun covers for math books, and I want to add them to my collection because I also need a good source for differential geometry that is not some course notes from the Budapest semesters and mathematics program that I still have. So anyway, Spivak aside. So Morse, he's studying these surfaces of negative curvature. Here are some examples of such surfaces. A geodesic flow is just a flow along curves of least distance along the surface. This is the way you can think about it. So the geodesics in the plane are just lines, right? And the geodesics on the sphere are the great circles. But when you have negative curvature, the geodesics are kind of weird, and that's what Morse was investigating, was, well, how can you walk around these surfaces along geodesics? And what Morse finds is that you can actually walk around these surfaces in a recurrent manner, and that you return to the same blocks, or you follow along the same segments of geodesics infinitely often. But these recurrence of these blocks is not a periodic recurrence, which is very weird. It's something that wasn't known prior to this, right? It's a lot of times when you think about repetition in dynamics or in physics, you immediately go to waves and periodicity, but that doesn't always have to happen. The way Morse talks about this in his paper, which doesn't have visuals and is thus actually kind of a slog to read if you're not someone who can think about things in the 3 dimensions or higher, is he has this sort of surgery process for investigating this. What you do is you have your surface of negative curvature, right? So here I've gone ahead and drawn an example on the board, and each of these surfaces of negative curvature has these bounding geodesics, which are these geodesics at the edges of these like cylindrical nodes of the surface. And what you do to do this surgery is you go ahead and pick a point on one of those bounding geodesics, and you draw a geodesic from that point to the other bounding geodesics, such that the geodesics that you draw are non-intersecting except for at the point you originally had P. Once you have these drawn to each of your bounding geodesics, you go ahead and cut up the surface by just slicing along this geodesic at these points, and then if you are cutting somewhere where you've already cut, you separate out the point as well. So when you're doing this with a surface that's not topographically equivalent to a cylinder or a warped plane or a Pringle, I guess is the best way to think about this. Pringles have negative curvature. That's the negative curvature plane is your Pringle. If you're not doing it with those two things, then this process gives you an even number of these bounding curves of the surface, which start and end at points that are associated or are equivalent to the initial P that you started cutting from. The reason that we want to do this is because we want to go ahead and unfold this surface and mush it around in a topographically nice way. And when I say topographically nice, I mean that the metric is somehow preserved, or the geodesics are somehow preserved when you go ahead and mush it around into a disk or square. And these, in this case, 4 bounding curves give you ways to glue the surface together a Z number of times. So Morse's process of cutting up the surface in this way and mushing it around and getting to the point where he can glue together the surface to itself in this Z product kind of way, and then using the Prouhet-Thue-Morse sequence, which he discovers in his own right, via a slightly different definition, is one of the first examples of the use of two-sided symbolic dynamics and its application to dynamical systems. So it's like got a lot of deep connections therein too, but I want to focus on, in this part of the video, of talking about how Morse defines it and then why you can get out this recurrent but not periodic behavior out of this thing. To do that, I need to talk more about the bit flip definition, or this alternative way of defining the Prouhet-Thue-Morse sequence. So to get at this bit flip definition and the almost recurrent, or the almost periodic property, which is this recurrent but not periodic property of this sequence, we first recall the recursive definition of the sequence, right? So m sub 0 is equal to 0, and m sub n is equal to m sub 2n, which is explicitly not equal to m sub 2n plus 1. So to form the bit flip definition, we're going to go ahead and define that b sub 0 is equal to 0, and then b sub n is going to be equal to b sub n minus 1 concatenated with the conjugate of b sub n minus 1. So by this construction of the b sub n's, the length of a b sub n is going to be equal to 2 to the nth power. And the claim is that if you do this bit flip definition forever, and you just keep on iterating this process, we have this new limit definition of the Prouhet-Thue-Morse word. And this is how Morse approaches it in his paper, although he doesn't use this like limit notation thing. So the claim is that the limit as n goes to infinity of the bn's concatenated with an infinite string of zeros is equal to the Prouhet-Thue-Morse sequence m. The idea behind this is actually has to do with, instead of right concatenation, which gave us the avoidance of the awawa, it has to do with left concatenation. Inside of a b sub n, so I'm looking at subwords of a b sub n for n greater than or equal to 1, then I know that b sub n in the jth position is equal to the conjugate of b sub n in the jth position plus 2n minus 1 by the recursive property that b sub n is equal to b sub n minus 1 concatenated with the conjugate of b sub n minus 1. And this happens for every j such that 0 is less than or equal to j, which is less than or equal to 2 to the n minus 1 power. The way to see this is that when you're taking a j that's less than 2 to the n minus 1, you can think of it as having a binary expansion with n minus 1 elements, and then when you're adding j and 2 to the n minus 1, what you're really doing in binary is you're left concatenating a 1. So for a more rigorous argument, if you go ahead and look at m sub 0, that's equal to b sub 0. And so m sub 0, m1 is equal to b sub 0 conjugate of b sub 0, because it's just 0, 1. And that's equal to b1. So that checks out. For the induction step, suppose that the nth term in the b sub n sequence is m0 up to m sub 2 to the nth power minus 1. Then when we concatenate on the next chunk of terms in the Prouhet-Thue-Morse sequence, what we see is that we have m sub j and then m sub j plus 2 to the n, which is equal to the conjugate of m sub j from our earlier observation that we're just essentially left concatenating a 1. So we actually have that the first 2 to the n plus 1 minus 1 terms of the Prouhet-Thue-Morse sequence is b sub n concatenated with the conjugate of b sub n, which is equal to b sub n plus 1, which completes the induction step. Again, that was more of a sketch. There are some things that I am being a little bit subtle about, but that's essentially how the argument goes. And so now we can talk about this recurrent but not periodic behavior. This has a definition called almost periodicity. That is, a sequence is said to be almost periodic or recurrent if any finite pattern w with the length of w being equal to n in the sequence appears within some finite bounded number of terms, big N of n. And this appearance happens within that many terms of when it was last seen. To see that the Prouhet-Thue-Morse word is almost periodic in this sense, what you do is you go ahead and look at some finite pattern that appears in the sequence of length n. And since you know that that thing is finite, and we have this now new bit flip definition that has this limiting property to it, what we can go ahead and say is that there is some k such that this finite pattern appears in a b sub k. And what you do after that is you go ahead and say, okay, well, it appears in this b sub k. Well, I want to look at what b sub k plus 2 looks like, because that will show up in the Prouhet-Thue-Morse word as well because of the limiting property. And then expanding that b sub k plus 2 according to its recurrence definition, you have what you end up with is a b sub k conjugate, b sub k conjugate, b sub k. And so since w appeared in b sub k, w reappears within 3 times 2 to the kth positions of when it last appeared, because each of those b sub k and b sub k conjugates has length 2 to the kth power. The last thing I want to say about this bit flip definition is that there is also a connection to substitutions, and I get to talk about turtles. So we can think about the bit flip definition in terms of replacing a 0 with something and replacing a 1 with something, instead of building these bigger and bigger and bigger words in the order of 2 to the nth power each time. So the substitution here is that 0 is replaced with 0, 1, and 1 is replaced with 1, 0. So this substitution is extended to words letter-wise. So we can go ahead and say that 0 maps to 0, 1, and then 0, 1 maps to 0, 1, 1, 0, and then 0, 1, 1, 0 maps to 0, 1, 1, 0, 1, 0, 0, 1, and so forth. And that this agrees with the bit flip definition from before. So what we get is we get this different notion of a limit here, where instead of doing this bn, conjugate bn, concatenated with 0 repeating and limiting that as n goes to infinity, we instead can limit as n goes to infinity of the substitution to the nth power applied to 0. And this will still give us an equivalent definition for the Prouhet-Thue-Morse word. Now, the reason I wanted to talk about substitutions was not because I wanted to talk about substitutions, which they themselves are like a very interesting, well-studied area of symbolic dynamics and combinatorics of sequences and all of that stuff. So there's like a lot of papers that are published in computer science journals and in dynamics journals about these things. But the reason I wanted to talk about them is because of turtle geometry. So Hal Abelson and Andrea DeSea write a book in the 1980s, or it's released in the 1980s, about turtle geometry, which is supposed to be this like programmatic visualization of mathematical processes, or like a way of exploring a way of exploring mathematics through a coded visualization. And it's one of the more popularized and accessible notions of this that are available out there. Nowadays we have things like Desmos and Desmos animations where we can animate math that way. But if you wanted to do geometry in this programmatic and visual way, turtle geometry would be a thing that you could do and you could code, and it's actually used as like exercises in a lot of computer science courses of like, oh, code a turtle program that will generate XYZ thing. And I remember doing these when I took computer science classes. I've had students that I've taught who have told me about their computer science classes where they do have turtle geometry problems still when they're like coding in Python and other things. So it's actually something that people do still, in terms of like it's an exercise that people use in the pedagogy of teaching computer science and mathematics. And so for us, we're going to go ahead and set F to be the forward movement by 1 unit, and L be the counterclockwise rotation by a fixed angle. In our case, theta is equal to pi/3. So the Prouhet-Thue-Morse sequence turtle programs of degree n, denoted by TMN and TMN bar, are defined by the words TMN is by definition equal to h of g to the n of 0, and TMN bar is by definition equal to h of g to the n of 1. And we can go ahead and look at a few images of what happens here, of how does this shake out. And you get this really interesting thing that happens where this thing looks like it is this thing, which is this famous fractal called the Koch snowflake, which is a fractal introduced by Swedish mathematician Niels Fabian Hegel von Koch in 1904. And so the Koch snowflake is a pretty important basic example in fractal geometry. It gives you a lot of different things that are not super trivial, but still complex enough where you can run through examples in a meaningful way. And so what we can ask is, well, do these Prouhet-Thue-Morse turtle programs actually approach the Koch snowflake in a meaningful way? There's a lot of stuff that I'm going to gloss over here because I am at the bottom of the pit of the weeds that I've dove into in order to distract from the fact that I started this video talking about chess and playing chess forever, and I'll get back to that in just a second. But I wanted to talk about this thing first in a very surface level kind of way. So the following very, very high level overview of what's going on here is courtesy of a paper written by June Ma and Judy Holdener back in 2005, where they apply properties of the Prouhet-Thue-Morse sequence in order to show that these Prouhet-Thue-Morse turtle programs actually approach the Koch snowflake in limit according to the Hausdorff metric. They do this sort of analysis at a higher level of generality, so they're not always talking about the Prouhet-Thue-Morse sequence, but the math that they do in that level of generality lets them conclude at the end that the Prouhet-Thue-Morse sequence actually approaches the Koch snowflake. So the question you first should have is like, well, what do we mean by close? And well, what do we mean by approaching the Koch snowflake? How are you drawing the Koch snowflake with these turtle programs? And the first question is, well, the Hausdorff metric, which I have a video on this channel. And that's what I mean by convergence, right? Is that they're converging in the sense of the Hausdorff metric, which means that they're converging in the sense of how close compact subsets of the plane are getting as you iterate this process of doing this turtle program over and over again. But I need to tell you how we make a particular compact subset, because if we just take what the turtle program spits out, there's something wrong here, because you're getting too much overlap for it to end up being the Koch snowflake, which is just a curve. So how are we actually drawing the Koch snowflake with this turtle program? And that's where the polygonal map comes in. So the polygonal map is going to go ahead and take this like high overlap setting of where the turtle program sort of like just draws over itself a ton of times, and it's going to associate it to a compact subset of the plane. And the idea here is that we just want to look at all of the finite words of zeros and ones such that there's a restriction R on this set. The polygonal map then is this K bracket dot thing, which is a map from these from a subset of this restricted finite words that we care about to compact subsets of the plane. And so this subset that we care about over S is going to end up being the language of the Prouhet-Thue-Morse word. So just the sequence of finite words that end up giving you the Prouhet-Thue-Morse sequence, which you can think about as just looking at the bit flip instances of the map. So again, there's a lot of math that goes into this, but it's a really cool visualization of how this stuff can be coded in a computer science setting. So there's a theorem, right? So Ma and Holdener actually prove that the Prouhet-Thue-Morse programs under this particular polygonal map, and there's a lot of stuff that's going on. It's very, very technical. But they do prove that this process does approach the Koch snowflake. And luckily, there is this blog post by someone who did like a coding challenge, which is based off of this paper, where they go ahead and show and provide code which implements the process described by Ma and Holdener to generate the Koch snowflake using the Prouhet-Thue-Morse sequence. I should chapter 11 this thing out to the end because we've been here for a while. So back to chess. How you play chess under Rule 13 is you go ahead and you implement the Prouhet-Thue-Morse sequence in the following way, via a substitution which takes alphabet letters of 0 and 1 to move lists on the board, or on the initial board of chess. So in theory, you can do what I say here whenever you have 4 pieces available to 2 for each player, where there's some like backtracking allowed and there are multiple options. So this doesn't work with pawns, but it works with basically every other piece set. But at the beginning of the game of chess, you can do this in particular with the knights on the board. So what you do is you go ahead and send a 0 to your first player moving a knight from G1 to F3, and then player 2 moving a knight from G8 to F6, and then player 1 moving their knight back to where it came from, and then player 2 moving their knight back to where it came from. And then a 1 is associated with player 1 moving their other knight from B1 to C3, and then player 2 moving their knight from B8 to C6, and then both players moving their knights back. It's a very boring way to play chess, honestly, and so you should really have a different rule to make sure that this doesn't happen. And nowadays they do. So instead of having these move repetition rules, like were agreed upon back at the first World Championship chess match, right? Or the first official World Championship chess match in 1886, now a lot of times it's more common to use state recurrence rules, which is where the game state of the entire board repeats a certain number of times before a game can be called for a draw. There are so many other things that I probably missed that I wanted to say. But yeah, there's a paper that John Conway is on and some other folks where they call numbers that have 1 mod 2 number of ones in their binary expansion odious, and they call numbers that have 0 mod 2 ones in their binary expansions evil, for even. It's a weird thing, but the idea is that there's it's like this alternative parity on base 2 numbers. A base 2 number can be odious or evil, instead of it being odd or even. Yeah, so Prouhet-Thue-Morse Sequence, it comes up all over the place. There are also, oh yes, this. There is this summary document, which this video was like the initial starting point for a lot of the research that was done for this video. And there's a ton more applications that they talk about in there, and also other relevant papers. And there's some algebra applications that I didn't have time to get into. Well, I mean, if you made it this far and you want to see me do more math stuff, and you like longer form things that go into, I hopefully I went into enough detail. I've watched like a handful of like Veritasium videos and other math-esque or STEM com channels where like sometimes they'll talk about stuff for a very long time and they don't go into a depth that is like satisfying to me. So hopefully I like tickled the brain a little bit if you're someone who enjoys rigor. And I know that I started this with chess, and I know that we all know that Stratego is the superior game. As always, I'm Nathan. You can subscribe to my channel for more math stuff. I'm also in a PhD program, so I have updates on that stuff here as well. Give a thumbs up if you have another topic that you would like me to cover in more of a long form content style like this. Let me know in the comments below. But otherwise, this one was so much chalk. It was enough chalk to be like what I do on average in a year, amount of chalk, but it was fun. So it was fun for me. I don't know about you. I like math, but yes, this was fun for me. So I will see you next time. Right concatenated of n, right concatenated expansion of n, right concatenated, concatenated, concatenated. Oh, I'm losing it. Okay,